Okay, so like today, like we'll discuss about derivatives, but with a different approach, like interpolation. Last class, like I told you about a bit of interpolation, right? So, so today will be like, sorry. Okay, so last time we had seen that if we don't have continuous function, rather we'll set of data points and ask a point to differentiate, like what's the derivative at that point. Okay, and that's our main goal to attack. Okay, so if fx is given as a set of discrete data, the method of interpolation can be very while computing the derivatives. Okay, interpolation, you know, right? If you have a set of data points, okay, say these are set of data points, then what you do in interpolation, you aim to divide, like connect each of these points, okay, by a polynomial. Is it? Yeah. So this is interpolation. Okay. So the same thing we will be looking at today's lecture. Okay, like each piece will be a polynomial. Each piece is a polynomial. So that's the meaning of interpolation. Now I give you a task. What's the difference between interpolation and regression? Okay, next class. So what's the difference between so I told you about what is interpolation. So what is the difference between interpolation and regression? So there is a very nice difference. So usually you might think that they are very similar, different. So in what way they are different? You know about regression, you know about interpolation last semester. So interpolation is a very basic concept which will be carried forward. So I urge those who are taking this course for the first time, like to at least brush up on bit of interpolation. Okay, bit of interpolation. Just go through some books and brush up on interpolation. That will be the very basics this course. Okay. Okay. So the idea is we have the derivative of the function, right? We have the derivative of say function fx, but we don't know the derivative, right? But what we know is the interpolating polynomial, because we are using the method of interpolation. So this is the interpolating polynomial or interpolating, yeah, polynomial. So now you know this interpolating polynomial, right? Because you have a set of discrete data points. Now you use the method of interpolation to find the interpolating polynomial. Now if you have the interpolating polynomial, your best guess for the fx. So now in order to obtain the derivative of fx, it's the same as obtaining the derivative of the interpolating. So derivative of the interpolating polynomial, derivative of interpolating polynomial. These are like, yeah. Okay. So you understand the basic logic behind this. So more importantly, since last class, you might have seen that we were taking equally spaced points, isn't it? So we were taking equally spaced points, data points, and then we were calculating the derivative. What's the derivative of the function at various points using forward difference method, backward difference method, or central difference method, right? At the last, we had a pinch of a thought about unequally spaced intervals. What happens if the previous spacing interval is a bit larger than the forward spacing interval? What about if they are comparably the same? What are the scenarios? Okay. But the main thing is we know the methods, numerical methods to solve or to find or to compute the derivatives of the function only with data points equally spaced. We don't know yet a method, okay, where the data points, if they're unequally spaced, how to compute. You can't use the method I discussed last class because that will give you a lot of errors. I just discussed that method to show you how, if you take unequally spaced points, then error might creep in. Okay. So now this method of interpolation can be really helpful. Okay, really helpful. derivatives for unequally spaced points. Okay. All right. So the idea is simple. What's the idea? The idea is first step, fit the interpolating polynomial, right? Fit the interpolating polynomial according to your data set. Okay. Then anyone can say, after you fit the polynomial, you have the polynomial. Then you take the derivative analytically. Take and compute the derivative, right? Okay. At that point, now, like I would stress also again that now you don't have a function that's given to you. Then you can apply the product rule, quotient rule, all those chain rule of differentiation. Now you have data, the set of data points, only the set of data points. Using the set of data points, how you will find derivative? That's what you were not knowing till last class, I guess. So that's the advantage of this course. Okay. Given a set of data points, how you will find derivative? Okay. Given a set of data points, how you will find the integration, all those things. But there is a limit for this process. Okay. What's the limit? The limit is the limitations. Okay. Is like you cannot use any, you cannot fit any polynomial of any degree. Like you cannot use you cannot use this method to fit a polynomial of say degree 7. Less than equal to degree 6 or 5, it will work nicely. So degree less than equal to 5, okay, it will work nicely. If you take larger, like higher derivatives, or sorry, higher degree of the polynomial, then there might be hidden oscillations in your function, okay, because it's a high degree polynomial. You can imagine, think of like the parabola, like it's a shaped. Then think of the cubic, it's like this. Think of like the x fourth, x fifth, and so on. Then you will see slowly how the oscillations they come into picture. Okay. Then you can see, like if you take higher degree polynomial, then there will be a lot of hidden oscillations. If there are hidden oscillations, the oscillations only are the main culprits while taking the numerical methods into picture, because those things you can't really approximate at some points, and that's the point where the errors will creep in and your method will be less accurate. Okay. So yeah, so notice that the method of interpolation is a local concept. Okay, it's not a global concept. Why I'm saying it's a local concept? Given a set of points, you can only apply to the few of those points only. Okay. Okay. So I will talk about two different interpolating techniques. One, I think you must have heard about like a regression technique, not the interpolating technique. A regression technique known as the least square, isn't it? Yeah, I think I discussed during last semester in data analytics. Least square, the R square test and all. Okay, so least square can be helpful. Then there is another method which is known as cubic spline interpolation. Okay. So the idea is pretty simple in cubic spline. Cubic and it's a spline. Okay. Cubic means you know that it will be order 3. Okay. So cubic spline came into picture in foreign countries. So what they did is they had this nails. So each dot I am putting is a nail. Okay. These are the nails. Okay, these are the nails. And what they did, if you have nails here planted all over the place, what you do, like I would try to join them, right? You try to join them. So using rope. So such a way that they don't slag. They don't slag. Okay. Think of your arrangement UK, like for the festivals, like Farewell Festival or something. I saw a lot of students, they were trying so hard to make it like, tension free. It should not slack. Like it should not be like this. It should not be like this. Okay, it should be tension tight. Okay. So seeing those things, it reminded me of this spline. Okay, so this is the concept you will see here. Okay, so given the set of nails, you are applying a rope. Okay, you are applying a rope, putting a rope here, so that it will be tension free, it will be tight. Okay, then definitely you can use interpolation. Okay, for this. Each 2 points there is an interpolation. Each next 2 points there is another interpolating polynomial. So on. Okay. So this is the basic idea of the cubic spline interpolation. Okay. So I gave you a bit of what do you call the basic idea. So basically it's a piecewise cubic curve. Why I'm saying it's not a single curve. It's made of these piecewise joint cubic curves. Okay. So after you approximate this thing, then what you will get? You will get polynomials. Okay. If you get polynomials, what you see in a polynomial? There will be coefficient multiplied by x to the power n equal to 3, right? So those coefficient you have to find. After you find this coefficient, yeah, you got your derivative. You can differentiate, right? So this is the basic idea. And what I want you to do is take as a project, okay, the cubic spline interpolation. Okay, this is very nice concept of difficulty. It won't be that smooth as forward finite difference, backward finite difference. It will be a bit tricky, but at the same time, it is such a topic that it will use Python, any programming language, and your math skills, like the calculations you do simultaneously. Okay. So by doing this project, you can like get a feel that how programming can come into this course. Okay. Till that, you might not get that idea. Okay. All right. So before we jump in, I'll try to I'll try to do an example. Okay. So we are given x. Okay. So take x like 1.5, 1, 2.4, 2.6. Okay. Are they equally spaced? Yeah. Are they equally spaced? Why? Hmm? Yeah. Difference between what? Ah. So you know that it is not equispaced. Okay. Can you apply the finite difference we discussed last class? That's the method we know till now. Can you apply? There we defined a step size h or delta x. The step size is defined as the first point minus the second point minus the first point x. Okay. So, but if you see here, you have 1.5, 1.9. The difference between them, then 1.9, 2.1. The difference between them is 0.2. So it's not equispaced. So what kind of things we can apply? We can use interpolation. Okay. So this is one of your exercises. Like first, I will perform this experiment using least square. Okay. Then second, you have to perform using the cubic spline interpolation. Okay. So first I will do using least square. Then cubic spline will be your exercise. Okay. So then let me know which one is better. Okay, either it is cubic spline interpolation or least square. Okay, all right. So what's the question? We have the set of data points. The question is, given the above set of data points, can you find the derivative at x equals to 2 and the second derivative at x equals to 2? Okay, that's the question. Okay. So I will try to do using the least square, like the interpolant I will use is a polynomial of degree 2. Okay. Suppose, I will say suppose I'm denoting P2x, denoting that it's a polynomial and it's degree 2. Okay, by say a0 x square plus a1 x plus a2. Is it fine? Hmm? That's a second order, second degree polynomial. Now your question is which 3 points you need to take? Which 3 points you need to take? See, this is a second degree polynomial. So you need, from your interpolation knowledge, you know that you need at least 3 points to fit this data. So which 3 points will you take from the given data? That's the next step. See, you need the derivative at x equals to, okay, x equals to 2 lies in between, say 1.9, 2.1. Okay, you can take those 1.9, 2.1, 2.4. That can be a good candidate, right? So we, given these 3 data points, we need to fit our polynomial. Okay. So yeah, we take the points. We take points 1.9, 2.1, 2.4, and we try to fit. Okay. Without going into much of technicalities. Okay. I hope you remember the normal equation for the. Oh, like I will write, just you can note the how the method goes. Okay, so it is like this: n, then sigma xi square, then there will be multiplication of sigma xi here, then higher order terms are coming in. Okay, here xi square will be there. Anyone has seen this? Okay, so I think so you understood, right? This is the what I am writing is the equation of the form ax equals to b. It's not the set of equations, but I'm writing the equation in terms of ax equals to b. Then what I will do, what's our aim after writing ax equal to b? To find x. Here, what is x? A0, A1, A2. What are A0, A1, A2? They're the coefficients of the polynomial. Okay. Then you will know the coefficients A0, A1, A2. That means you know the polynomial. Then you can differentiate it too. Then you can take the second differentiation also. So that's how powerful this method is. Okay. So the right side will be like sigma yi, all the sets of these fxi points. Okay. Then sigma xi yi. Then multiply again once more sigma xi square yi. Okay. Now I ask you to do this calculation now. Okay. So after this, I hope you have done these calculations. I hope you have done this calculation. So just try to check. Just try to check. This is 3. $13.78. Is it 6.4? Then again 13.78. 29 point. Then what is the right hand side? 4.67. 42. Okay. 10.05. Then so your job is to find A0, A1, A2 from now. You can do that. Okay. So just I will write what I am getting here. But you should try to find how to do the matrix calculation using the calculator. Because it might come, then you're stuck here. How you, it's not very sweet equations like 2, 3, 2, 3, 4 integer coefficient where you can just multiply. These are like decimal coefficients. So doing the simultaneous equation will be a tough. Therefore, we are doing the matrix. So A0 you will get minus 0.7714. A1 will be 1.5075. This I want you to check. Is this correct? Minus 0.1930. Okay. So then you have the polynomial, right? Then you can take the derivative of the polynomial also. 2a2x. Isn't it? Yeah. It was a second order. Then you differentiated analytically. A1 plus 2a2x. Now what is A1? 1.50. 2 times A2 minus 0.1930. What is x? At which point we want to evaluate? 2. So P naught, P prime 2 it should be. Okay. So then this value would be how much? Check like it should be 0.7355. Okay. Similarly, you can calculate P. Okay. What it should be? Take the derivative again. It should be 2a2. Isn't it? Irrespective of any x. So for any value P2 double prime of 2, it will be 2a2 only. Because there are no x involved. 2a2 means a2 means here what? Minus 0.1930. What is that value? Okay. So using cubic spline interpolation also you can do this. This is the second part of the question. But after you do the project, I urge you to attempt this question. Okay. Cubic spline interpolation. How using cubic spline interpolation you can do it. By intuition, we can guarantee that cubic spline interpolation will be a bit more accurate as compared to the squared polynomial because it's a cubic polynomial. It can fit much better, right? So try and let me know, okay? So in the notes, it will be there. The equation is already solved using cubic spline interpolation, but your job would be to explain the cubic spline. One, using the analytical method. Second, using the Python, okay? All right. So, okay. Now I want to come to another method, okay, which is not that helpful. Like the two methods we have learned are very powerful actually. The two most powerful methods. One is the forward finite difference, backward finite difference, central difference for equispaced data. Okay. For unequally spaced data, you can use this interpolation, cubic spline, or more easier would be to use the second order polynomial, second degree polynomial, okay, using the normal equations. So I would like to stress that this set, what I have written here, where it came from, it is the normal equation. You search for normal equation degree 2 polynomial. So it doesn't matter, it has not been covered in last semester or something, but just refer and know this. Okay. Writing that matrix is only the key thing. After that, done. Okay, so yeah. And also I forgot one more thing. If you see, you can't guess because it's non-trivial, not trivial. Okay. The data which we got here, the data which I have written here like x f x, it has come from a function, a continuous function, fx. That is x square e to the power of minus x by 2. Okay. So you can analytically calculate the derivative and find the derivative at x equals to 2 and check what you have gotten numerically. All right. So here, if you compute analytically, this is analytically, okay? Analytically, I found the derivative using product rule because x square is multiplied by e to the power x minus 2 and I can use the product rule, okay? F prime of 2. F prime of 2, I am getting 0.7358, okay? And we got 0.7355. So you can see it is accurate up to 3 decimal places. You can guess how powerful it is. Okay. F double prime of 2. It will be minus 0.3679. Here we ran a bit in a loss. Okay, because it's accurate up to just 1 decimal place. It is minus 0.3860 numerically, but analytically it is minus 0.3679. And it is explainable. Why? Because higher you take the higher order derivative more and more, higher you go, triple derivative, fourth derivative, you will encounter. Okay. Okay, so next, yeah, I want to cover like just one more technique. It won't be what you call like compulsory technique, but I just thought that you should know. I was not planning to cover this because you already knew the two powerful methods already. So you don't need to know this method, but still you might, in many books, you might see this notation. Okay. This is where a bit of confusion arises. A bit of confusion, like which method should I use? Therefore, I taught you the first two power of methods. Then I am coming to this method. Okay. So this is known as like the Newton's forward interpolation formula. Okay. All right. So here in this method, you will see operators. Okay, like this or this. Okay. Yeah. So what are this? So you already know, is it? We'll cover this. So, okay. Again, function, say y equals to fx, okay? And not that we are given a function, we are given the data points. Say we are given n plus 1 set of data points, not just any data points, equispaced. This is where lot of abilities are being dragged down because equispaced. You can't be guaranteed that this method will work for non-equispaced points. Okay. So this is for equispaced points. Say I denote any equispaced point xi as x0 is the starting point plus ih. H is your step size, isn't it? And you have corresponding to each xi, you have a yi. Gotten? So n plus 1 data points, that means it will run from x0, x1, so on till xn. And y0, y1, so on till yn. Right? Given these data points, how you will find derivative. So this is a very nice method also. Like graphically, it will not take much of your calculation time and it is very graphical. So yeah, This is the Newton forward. I think you must have encountered this in your last semester because you already know this delta. This delta I will be, anyone? Delta y, I suppose it will be yi plus. So this is the formula for the forward and backward operator, the delta and nabla. Okay. So y equals to fx. So you already know from your previous course that it looks like this. I will just write it down. Like those who don't know this one, I urge to look into the some books. Okay, this is the basic thing we need to start with. So on. Okay. Now you can take the derivative y prime, that is f prime of x. Okay, how it will look? So you just need to differentiate. Okay, I will just write it, but then after that I will explain why we get this expression. Okay, this of the students, they don't go into deep how you come from here to here. So obviously it will be delta 2 y naught because we are taking a derivative again, and there are some other terms also which I'm skipping for now. It's very high order term, but you cannot refer the notes I will share. Okay. So similarly, you can find the double derivative, that is the f double prime of x. Okay. So again, 1 by minus 1 by x square. Now delta 2 y naught plus. Okay. All right. So you have these formulas. So in order to find the derivative, what you need to do? You need to find y naught and so on. After you have these coefficients, you are done. You can find the derivative at any point. So this is where I'll show you an example. Okay, you just need to get the example, then you can appreciate the theory better. Sometimes getting to the theory directly might not help. You need to do some example, then you can appreciate the theory. So how we got from y to y prime? So what is y prime? Y prime is dy by dx. So what we can do? Can you do this? Dy by du, du by dh. Yeah? Just take this hint. Take this hint. Therefore, due to this reason only 1 by h is coming outside. Okay. Suddenly, it might not be trivial why 1 by h is coming outside, but due to this chain rule, it is coming. Okay. You should counter me. Okay. So we'll see. I don't want to go into more deep for this example because this is you can apply this method or you cannot apply this method. Up to you. You can or cannot, up to you. But the first two methods are very much powerful. Okay. So see, for this question is like find dy by dx and the double derivative d2y by dx2 at x equals to 1. And x equals to 1 is your first point already. It's a tabular point. It's a tabular point. So usually for this method, like for the using Newton's interpolating formula, you need to construct a difference table. This is known as a forward difference table. This is known as a forward difference table. Okay. You write the y in the second column, then you take delta y. What will be delta y? It will be 5 point yi plus 1, 5.6665 minus 5.4680. That you write in the middle of them. Okay. Then you do 5.9264 minus 5.665. That is here. That is here. So you generate delta y. Is it clear? Then what you do? Generate delta 2y. Now, how you will generate delta 2y? You need to take the difference between the deltas. Okay. So 0.2599 minus 0.1985. Okay. Then you have this. Then again you do delta 3y. So you like notice as you are taking more deltas, your points are getting decreased. Number of points. But here we are happy with taking delta 3y. You can take also delta 4, up to you. Okay. Then what you will do, you have, see, for one, like I will show you the next one. Oh. So there should be another slide I missed. But after this, the job would be to use this formula. The job would be to use this formula, delta y naught, delta 2 y naught, and so on. Okay, because you have these guys, right? From this, you have these guys, delta y, delta 3y you have. So you can correspondingly just apply, put this coefficient in, and you'll get the derivative. Okay. So again, this is another example. I urge you to go through this example and try by hand. Therefore, I have given the solution. Okay, I should not have given. Only you know I have given the solution. Okay. So take this data set now. Now it is asking the question that obtain the derivative at 1.1. Is 1.1 in your data set? Yes. No. 1.1 is not in your data set. So how you will approach this? 1.2 is your data set. It is there. So it will be easier. Okay. Another question, in this method, if the point where you are computing the derivative, okay, is listed as a data point, then your life becomes easier. The formula simplifies a lot. Okay. But if it is not lying in one of the data points, then you have to apply the general formula. Okay. So all these things I am telling to you after doing calculations. So only after you do the calculation by your hand, then only you can understand this, what I am saying. Else it will just swing. Okay. Okay. So again, constructing the forward difference table, I will leave it to you why we are showing these arrows. Why are we showing these arrows? You communicate next class to me. Why are we showing these arrows? Why? Then nothing is there. Like at C at 1.1, they are just applying this. dy by dx is 1 by h. This formula we have seen, right? Instead of p, I think we used u. Yeah. And we just applied the formula. Isn't it? The disadvantage of this is you need to memorize the formula. That's the only disadvantage in this. And memorizing this is a bit tricky, not tough. During my master's exam also, I memorized this and I gave the exam. Okay. So, but personally, this is not my method. Okay. Not my method, but you can easily do this. You can easily do this. If you have a good of calculator experience, you can easily do this. Okay. So similarly, backward difference also you can do. Nabla x, Nabla x, Nabla 2x, Nabla 3x, and all those. This is an applied example. Like, you know, derivative is like velocity. If x is position, when you take the derivative, it becomes velocity. Take the derivative again, it becomes acceleration. Okay. So this is the same question. Find the velocity and acceleration of the slide time equals to t equal to 6. So this is a very good example. This is a very good example, real life example, where you, even if you know how to apply or compute derivatives analytically, but still, if you don't know numerical method, you can't solve. So this is the one of the advantages of knowing numerical methods. Okay. So these are the examples like I'm giving to you so that after you go home, at least you try these examples out. The best advice I can give it to you is after each of the class, spend around 1 or 2 hours or 1 hour 30 minutes, definitely after this class, throughout the day, and do whatever is being taught. Then it will be printed in your mind. it will be printed, believe me. That way, like I also remember I missed one class. I did not come to one of my numerical method class, and I till now, till this date, I find that method a bit scary. So therefore, yeah. Anyway, so this is the backward difference, backward Newton. So Newton backward interpolation formula, okay. So these two methods are easily doable, okay. But you need to work on it by yourself. Then only you can appreciate this. Okay, let me know. Like I think I will give an assignment today. Okay, consisting of 3 to 4 questions, and you have to submit. Okay.